Right now, there is a distinct mathematical probability that a hyperdense object is tearing through your immediate environment at 136 miles per second. It makes no sound, it reflects no light, and it will pass right through the floor without leaving a trace. Physicists suspect these anomalies are primordial black holes, swarming through our solar system in numbers so vast their combined gravity dictates the motion of galaxies. For 50 years, astrophysicists have been hunting for dark matter, the invisible substance that makes up roughly 85% of all the mass in the universe. We know it exists because we can measure its gravitational pull on stars. But after half a century of lowering highly sensitive detectors deep underground, scientists haven't found a single particle. Curious, slightly hushed. That string of failures pushed researchers to look backward, to the first fraction of a second after the Big Bang. Before stars even existed, the universe was a violently hot, dense soup. Because these objects were squeezed just slightly too tight, it collapsed. Raw gravity forging a black hole without the need for a dying star. A primordial black hole presents a physical paradox. Its event horizon is subatomic, smaller than the nucleus of a single atom, but crammed inside that impossibly tiny point is the mass of an entire mountain. Researchers focus on a specific bracket called the asteroid mass range. These objects weigh anywhere from 220 billion pounds to 220 trillion pounds. Based on the sheer density of dark matter measured in the Milky Way, mathematics dictates that at least one of these ultra-heavy subatomic black holes is flying through the inner solar system right now. Because these objects are smaller than an atom, we cannot use traditional optics to find them. If we want to catch one passing Earth, we have to track their gravity. Tracking invisible objects by watching how they pull on visible planets is a proven scientific method. In 1846, French mathematician Urbain Le Verrier realized something was wrong with Uranus. The planet was wandering off its orbital path for no apparent reason. Le Verrier knew the laws of orbital mechanics were ironclad. If Uranus was wobbling, an unseen mass had to be yanking on it. Using only a pen and paper, he calculated exactly how heavy that invisible object had to be and where it was hiding. He mailed his equations to German astronomer Johann Galle, who immediately aimed his telescope at the exact coordinates Le Verrier provided. Galle found a brand new world right where the math said it would be. This was the planet Neptune, a world discovered entirely through gravitational deduction before a human eye ever verified it. Gravitational perturbation proved to be a reliable forensic blueprint for finding the invisible. To find something hiding in the dark, you watch what it pulls into the light. In September 2024, a team of researchers at MIT proposed running Le Verrier's exact playbook again, using Mars as our modern-day Uranus. Identifying a black hole requires looking for cumulative effects. Imagine two cars driving side by side on a highway at identically matched speeds. If one car instantly loses a fraction of a mile per hour, the drivers won't notice a difference in the moment. When a primordial black hole rips past Mars, its velocity changes by a fraction of a millimeter per second, unnoticeable in the moment. But over a decade, this microscopic change compounds until Mars is 3 feet away from its predicted position. We can measure that 3-foot gap. For over 20 years, satellites orbiting Mars have been bouncing light signals back to Earth, using atomic clocks to calculate the distance between the two planets with sub-meter precision. Physicists have weaponized the 140 million-mile gap between Earth and Mars into a highly precise scientific instrument. Differentiating the gravitational pull of a black hole from the noise of thousands of normal asteroids requires looking for a very specific signature. Moons and large asteroids obey local traffic laws. They orbit relatively slowly and remain strictly within the flat horizontal plane of the solar system. A primordial black hole is an interstellar intruder. It enters our system at blinding speeds, often striking from highly erratic angles. While an asteroid pulls Mars forward or backward along its usual path, a black hole cutting through at a steep angle will yank Mars vertically out of the orbital plane. Researchers are currently scrubbing 20 years of historical telemetry data to find this specific vertical wobble. They believe the data could hold up to 5 individual signatures. Isolating this orbital inclination change would provide the first physical proof of dark matter. This raises a terrifying question. What physically happens if one of these mountain-weight anomalies collides directly with Earth? The subatomic size of their event horizons makes them essentially harmless. Because the black hole is smaller than a proton, it is too tiny to interact with the atoms that make up normal matter. It would slice right through the Earth without an explosion, a crater, or a sound. It would pass through the planet like a high-speed bullet passing through water. We inhabit a cosmic shooting gallery of ancient, harmless phantoms. The final proof of their existence is currently hidden in the subtle movements